Thank you. Thank you very much, and thank you for giving me the opportunity to present this work in this very nice event. The city is great, the organization is great, thanks a lot. So this is joint work with my colleague Jérôme, Tam, and Eric Moulin, and I'm talking about subgradient with errors in the semi-algebraic setting, and I think this is a good occasion to mention that the geometric approach to optimization has been very fruitful, and this has been mentioned in many talks, and I think that this guy had a pivotal role in introducing these ideas. So this is our problem. We consider minimization of a Lipschitz function. It's not necessarily smooth. And this is our method, subgradient algorithm, but I add on top of that an error, which is of magnitude at most epsilon. So throughout the talk, epsilon is positive, and it denotes an arbitrary error that can be chosen arbitrarily at each iteration. The notion of subgradient that I'm using is the Clark subdifferential. I recall the definition, and there is a very important remark to be made. In most cases, the Clark subdifferential is not meaningful. It does not carry a meaning, and this is correct. And this allows to emphasize this semi-algebraicity assumption. I'm only considering well-structured objects. And for well-structured objects, the Clark subdifferential still has meaning, and there are many things that we can do with it. So we stick to this because it simplifies some technicalities, and also it allows to capture subsets, stronger notion of subdifferential eventually. So the most important thing is that epsilon doesn't go to 0 as k goes to infinity, and let's talk about it. So what is the motivation for this? So nowadays, we optimize complicated functions which may involve, as subroutines, minimization problems or numerical integration, or we may use smoothing techniques. And all of these things may introduce systematic error that we do not really control. So think about an optimization algorithm that you need to stop before reaching the asymptotics. There is a small error, and it's not always possible to control. The second motivation is numerical error. We all love to prove theorems about real numbers, but they do not really exist in the digital world. What we end up doing is floating point arithmetic. So this is the standard for numerical analysis. In machine learning, the standard is actually this. And if you're fancy and using low memory training methods, you may be using those more, let's say, complicated floating point formats. And the last bit of motivation is empirical risk minimization. Let's say I have a small subpopulation which can behave arbitrarily, okay, and adversarially. I want to control to understand what is the most pathological effect of this adversarial population, what it could have on my algorithm. Those are the motivations. I will not come back to this. The story is not new. The robustness to error has been around since the early developments of non-smooth optimization, non-smooth methods. The work that is the closest to ours is by Solodov and Zavriev in the 90s. It's general result about non-convex optimization. And this has been extended in various settings. I'm not going into the details, and of course, this is not an exhaustive list. Okay, so what's new? What do we have? The main thing that we have is we leverage the semi-algebraicity assumption, which allows to characterize all accumulation points of our sequences, which is a new feature in the non-smooth setting. And also, we are able to consider both vanishing and constant step size, and we have seen several talks mentioning the relevance of constant step size in optimization nowadays. So this is our main result. Again, the setting, the algorithm, and I need a bit of assumption on top of that. This is a boundedness assumption. So this set is called the epsilon critical set of F. Okay, it's the set of points such that there is a subgradient with norm at most epsilon. So if you pick epsilon equals 0, you get the usual critical set. And this is like the extension for epsilon strictly greater than 0. And I want this thing to be bounded. Okay. So this is a boundedness assumption, and this is actually stronger than coercivity. This implies coercivity. It's not direct, but it implies coercivity. So I require coercivity plus boundedness of this thing. I don't want square root-like behaviors with the function going to infinity, but the derivative going to 0. And those are the only assumptions that we have. Okay, so throughout the talk, those are our assumptions. We can say the following. Under those assumptions, there are three numbers. The first one gives us an interval of admissible epsilon values. So I'm talking about small epsilons. And we have two regimes. So we could consider vanishing step sizes. And in that case, we can say that the sequence will eventually fluctuate around the critical set. So the usual critical set, crit 0. So we have errors in the algorithm, but we measure the distance to the usual critical set. And we can estimate the distance by a certain power of epsilon. Yes. Yeah. So I have an interval of admissible values. This one, the same, Clark. Again, we use Clark because it simplifies some of the technicalities. I need Clark for, I could do better. Maybe we didn't work hard enough. I don't know. The thing is, I'm only able to talk about this for today. Okay. And second result, constant step sizes. Now the sequence will depend on the step size, and we have the same asymptotics. The distance to the critical sets is bounded by the same quantity, but we have two limits this time. We have an asymptotics in k as k goes to infinity, and we have the limit for small step sizes. So we let first k go to infinity, and we let k alpha, the step size, go to 0. So I would like to give you some elements about how we obtain this. So first I will talk about a discrete Lyapunov mechanism, then flow invariance, and then I will explain how we leverage semialgebraicity. Yes. Is it? Oh yeah, okay, sorry. Okay, actually it's lower bounded. I just, okay. Yeah, bounded from below. I need this. Okay, so this is an assumption, and I choose the bound to be 0. This is arbitrary. So sharp. So let's understand stationary points. So this is a single iteration of our algorithm. This is again our epsilon critical set, and it's easy to realize that if you pick x0 in this set, then it's possible to pick x1 equals x0. So this is exactly the set of stationary points, meaning the set of points where you may not move. That's how it looks like on the picture. So on the top, you have a function. On the bottom, you have its derivative, and you have in columns certain values of epsilon. So the epsilon critical set corresponds to values in the middle band, horizontal band here. So you have small intervals on the x-axis. You can copy them above, and you get interval of function values. If you increase epsilon, this band increases, all the interval increases. At some point, they merge. So we had 3 intervals, we have 2 of them now. 2 bigger intervals, and at the end, we have only 1 interval. So this is how it looks like and how it depends on epsilon. So this epsilon critical set is the set of stationary points, and actually it's more than that. If you pick any epsilon prime strictly smaller, you can move arbitrarily in a connected component of this epsilon prime critical set. You can move in any direction. The sequence can do anything because of the arbitrary perturbation here. Okay. Now let's understand the opposite direction. What are the non-critical points, let's say. So I repeat, again, this is the algorithm, my epsilon critical set, and I introduce this notation, the epsilon critical values, which is just the image of the critical set by F. And the elements which are in the complement will be called regular, epsilon regular values. And it turns out that those epsilon regular values are actually repulsive. Okay, so intuitively, this makes sense. So let's say here you pick these values, 0.5, and the corresponding x here, the derivative is above 1. Okay, so if you had a perturbation of magnitude 0.1, then this will remain positive. So it means that if you follow the direction here, you will have to get down, no matter which perturbation you choose, and you have to do it until you reach this interval. And it's possible to make this rigorous. So in the non-smooth setting, we have a bound, an upper bound on the step sizes, such that if you pick any sequence, independently of the initialization, with step size upper bounded by alpha bar, non-summable, then at eventually the function values will avoid this value L. So it will stay above or below forever after a finite number of steps. And from this, you can deduce the following. The function values will be attracted by the epsilon critical value. So in the small step size regime, we have this usual limit, and in the constant step size regime, we have this double limit. And this is the result which is natural, and it was actually already present in the Solodov paper for under slightly weaker, stronger assumption. Right. Continuous flows and invariance. So in order to talk about invariance, I need to introduce this differential inclusion, which is the continuous time counterpart of the algorithm. So the notion of solution is here a Lipschitz function such that the inclusion holds for almost all t. And this has been widely studied. You have textbooks about that. Such solution always exists. They may be not unique. Right. What is an invariant set then? An invariant set is a set such that for any x in the set, there is a solution to this which goes through x and which remains in S. And you can pick gamma 0. So gamma will be the solution. Gamma 0 equal x, and the image of gamma is in S. So you may have several such solutions. We require that only one of them stays in the set. And this is a very relevant notion because there are two important sets related to our problem which are invariant. So if you pick vanishing step sizes, then the set of accumulation points of the sequence will form an invariant set. Meaning this is not our result actually, this is due to Benhaim-Bauer-Sorin in 2005. What we had here is a similar result for accumulation set for constant step size. So this is exactly the same idea. We look at accumulation points as k goes to infinity, but we take care of the step size using this complicated union closure intersection. Okay, but this set S will be invariant. So what this set means essentially is very, I mean, up to almost no approximation, it means this. So I'm considering for a fixed alpha the accumulation points as k go to infinity. I have a set of accumulation points, and then I'm looking how these accumulation points accumulate as the step size go to 0. So those are accumulation points of accumulation points, and this form an invariant set. And this is, let's say, a contribution of this work of independent interest to notice that this thing is invariant for constant step sizes. Okay, so I just copy-paste this result. We have two invariant sets, S1, the set of accumulation points, S2, the set of accumulation points for constant steps. That's what we have. What we have seen right before was the fact that epsilon critical values were attractive for the function values. And if you merge those two, you get the following. S1 and S2 are invariant, and their image by F is included in the epsilon critical values. Okay, so that's it for the analysis of the algorithm. Now we need to understand what we can say about this. Right, so we will use semialgebraicity a lot. Again, the question is, S is invariant, its image by F is in the epsilon critical set. What can I say about S? In general, I cannot say much, but for well-structured objects, we can say a lot more. So the reason is that a typical Lipschitz function looks like this. It's oscillating. It has, for example, local minimizer as a dense set along the line. It's very bad. This is a semi-algebraic function. It's non-smooth, but it's well-structured. It's non-smooth in a very nice way. I recall the definition for the record. A semi-algebraic set can be expressed by finitely many polynomial inequalities, and a semi-algebraic function is a function whose graph is semi-algebraic. But what is important for us is not the definition, it's the wealth of qualitative properties for which this definition is a sufficient conditions. So we have a lot of things: Holder continuity, KL inequality, Sard property, many things. This covers many applications, and if you want to go beyond polynomial, we could extend this to definability in minimal structures, for which we have similar properties and which covers virtually all applications that I know about in signal processing and machine learning, for example. Right. Okay, so this is the challenge. My set S is invariant. Its image by F is in the epsilon critical value. So let's pick a function. Here you have the 3D plot. Here you have the contour plot. And in gray, you have this epsilon critical set. So this is the set of stationary points, but also this is a set in which you can move arbitrarily. So you can start from this minimum here. You can go up, for example, go down, but you can also get out of this gray set. You cannot go out here because the function would need to increase, but you can go out here and then decrease and get back to the minimum. But you can also go out here and decrease and get to a new connected component of the epsilon critical set. So we will not be able to show that this epsilon critical set is attractive for the method, because this is wrong, the curves, the solution curves, or the algorithm can get out. It can do things, and that at some point maybe it will get back. So we need to understand this. Okay. So for this, we need a few tools. First, chain rule along Lipschitz curve. So this is from Davis and colleagues. For any Lipschitz curve, the time derivative of f along the curve is given by this formula for almost all t. So if f was continuously differentiable, we would have gradients here, and this would be the usual chain rule. Here we have non-smoothness, so we get this almost all t here, and the for all quantifier for the Clark subdifferential here. This is the thing that we need. How do they obtain this formula? Essentially, they use the variational projection formula of Bolt and Lidis, Lewis, and Chiota from 2007. The idea is the following. Here is a non-smooth function. It's smooth everywhere except along this dotted line. And if you pick gamma here, the blue curve, which is Lipschitz, it may cross this dotted line, let's say transversally, but this would not matter because we only care about almost all t. So this would be, let's say, a single t. Eventually, it would get stuck in this along this dotted line. And along this dotted line, we can precisely use the connection between the subdifferential and the variations of the function restricted to this dotted line, which is the projection formula by Bolt and colleagues. I'm not going into the more details. So what can we deduce from that? So let's pick a solution curve to our differential inclusion. So gamma dot will be minus v plus e, v in the subdifferential, e an error of amplitude epsilon at most. And let's assume that we do not reach the epsilon critical set. So this distance is lower bounded by something that is strictly greater than epsilon. In that case, we can obtain a bound on the variation of the function just by integrating the time derivative. Okay, so here we get gamma dot times v, but gamma dot is of this form, and this is for all v. So I can pick here the v, which is vt. Okay, and in that case, I get minus v squared plus epsilon times v, and here I use Cauchy-Schwarz inequality and the fact that e is of norm at most epsilon. And using this, this will be smaller than a certain quantity, which is strictly negative. So this is how we obtain Lyapunov decrease for our differential inclusion in continuous time. And this was actually the basic to obtain the discrete time Lyapunov decrease that I mentioned earlier on. I just copy the implication that we had. The inequality is reversed, but this is the same implication simplified. Getting back to our original question, if I pick S invariant with its image by F in the epsilon critical values, what can we say about S? So a small step more, an additional step, using semialgebraicity, the epsilon critical value can be decomposed as a finite union of intervals of this form, bounded intervals. So the only thing that we will study is solution to the differential inclusion, which image by F is contained in an interval. Right, that's the only thing that we study. And using essentially the contraposition of the implication above, we can deduce the following. For any delta strictly greater than epsilon, you need to reach crit delta by a time at most this. So here you get the length of the interval, and you get delta, which is here strictly greater than epsilon. And the reason is if this doesn't happen, essentially this would contradict this implication. And now we're almost done. Why? Because this allows to obtain uniform control between any point in S and the delta critical set. Why is that the case? If I pick x in S, then there is a solution curve which goes through x at time 0. It needs to reach crit delta by this time here, and it travels in space with speed at most L plus epsilon. So it needs to reach crit, this means that the distance between x and crit delta is at most this. So the upper bound on time, the maximum possible travel speed. Right, so, and this is uniform for all x in our set. And this allows to deduce the result that I mentioned at the very beginning. So we have a similar bound, which is uniform for x in S. This time, the bound is on the distance between x and the usual critical set, the zero critical set, and the bound is of the exact same form as I mentioned. How do we obtain this? We relate A and B here with delta using the Kurdyka-Loyasevic exponent of F, and we relate crit delta and crit 0 using the Holder metric subregularity exponent of the partial subdifferential. Both those things exist. The technicalities do not matter. This is just to tell you that this row is connected to quantities which have a geometric interpretation. Right, and now wrapping things up, we have those two sets which are both invariant and whose image is in the epsilon critical value. And using semialgebraicity, we can say that for any such set S, okay, the supremum of the distance between X and S, between X and the critical set, supremum for X in S, will be bounded by this estimate that we have. And so this is how we obtain our conclusion. Right, so let's conclude. This is our problem, our assumption. This is the method. Essentially, we show that the sequence with either constant or vanishing step size will eventually fluctuate at a certain distance from the critical set, and the distance depends on epsilon. This is a reference with the details of the result that I mentioned. And with this, I thank you for listening. And if there is any question, I can answer.